Welcome to another lecture in the course on 3G and 4G wireless communication systems. Last lecture we started our discussion, that is we continued our discussion regarding advantages of CDMA cellular, that is what are the different advantages of using CDMA as a cellular technology compared to previous technologies, and we said one of the important advantages of CDMA is that CDMA results in what is known as graceful degradation. And why is that happening? If you remember, we said the interference caused by an addition of a new k plus 1th user is distributed equally amongst all the existing users. That is, this new user is not adversely affecting one particular user, but his interference or the adverse environment caused by him is shared equally by all users, which means each user's SNR decreases by a small amount rather than one user getting hit severely and other users not being affected. So, this results in graceful degradation, which is a very important property of CDMA systems, and that in turn has a very powerful application in CDMA systems, because this means now that the interference caused in the adjacent cell by the use of the same frequency band in the adjacent cell is not affecting one user, but it is shared by all users. Hence, this means each frequency band can be used in every cell in a CDMA, thereby a much more number of users can be supported in a CDMA system compared to 2G systems such as GSM and 1G wireless systems. Hence, this factor or this effect which enables use of all frequency bands in all cells in CDMA is known as universal frequency reuse, and that results in enhancing the capacity or enhancing the number of users that can be supported in a CDMA system manifold. In the case of GSM, we saw that in a GSM system only 1/7 of the frequency bands can be used in every cell, which means in CDMA, since you can use every band in every cell, that results in a 7-fold increase in the number of users that can be supported, because number of users, because bandwidth is directly proportional to the capacity of the system, alright. So, bandwidth that can be used in every cell increases 7-fold, which means the number of users that can be supported or the data rate, the net data rate of all the users increases 7-fold. That is the big advantage of CDMA systems. And we started with another advantage of CDMA systems, which is related, which is multipath diversity. Previously we said existing cellular standards, remember we started our discussion with cellular communications. We started with the notion that there is multipath propagation. For instance, if you remember what we said earlier, we said that if there is a base station in a wireless system, then there are multiple paths through which the signal reaches the user. Now, these paths can add up either constructively or destructively, hence they can cause constructive interference or destructive interference at the user. So, that was not, it was not left to the user's choice to decide whether these paths add up constructively or destructively. This is known as multipath propagation, and we said this is known as multipath interference. So, this causes multipath interference in a normal wireless system. However, in a CDMA system, we said because of the very interesting nature of the CDMA system, one can now extract these multipath components. So, one can extract these multipath components and always force them to add up constructively. That is what is resulting in diversity. Again, this is known as multipath diversity. This is a big advantage in CDMA, because previously what was destructive interference can now be intelligently converted into constructive interference, thereby resulting in significant gains. For instance, we said in a CDMA multipath system, the multipath channel can be expressed as having L channel taps H0, H1 up to HL minus 1, and the output signal Ym can be expressed as H0 xm plus H1 xm minus 1 plus H2 xm minus 2, so on and so forth, plus HL minus 1 xm minus L plus 1. So, we have in Ym, that is signal received at time n, we have contribution from xm, but we also have contributions from xm minus 1, xm minus 2, xm minus L plus 1. This is precisely inter-symbol interference, because the current symbol is being interfered by L past symbols. Now, in a CDMA system, because of the nature of the CDMA system, at the output what I can do is something interesting. I can take the received signal R of m and I can correlate it with C0 of m, that is the chip sequence, and that will give me symbol S0 times h of 0. Remember, this h of 0 is nothing but the coefficient corresponding to the 0th path. This is the coefficient corresponding to the 0th path. Hence, by correlating with C0 of m, I am extracting the path corresponding to h of 0. That is what I am doing here. Similarly, I can correlate with C0 of m minus 1, which is the shifted chip sequence, and that extracts the path corresponding to, that extract the signal corresponding to path 1, which is S0 H1 plus N1. So, this is essentially extracted by correlation with C0 of m minus 1. So, by correlating with the shifted sequence, I can extract the path corresponding to channel coefficient H1. Similarly, I can correlate with C0 m minus 2 to extract the path corresponding to h of 2, and so on. I can have L minus 1 paths. By correlating with appropriately shifted chip sequence, I can extract the signal corresponding to path L minus 1. Now, once extracted, having extracted these paths, these can be coherently combined. How do I combine them? Although I went over that in the last lecture, let me again go over that in today's lecture, so that I can reinforce that point. So, let me start today's lecture with a brief repeat of how we extracted multipath diversity. So, we said R0 is the signal after correlation with C0 of m, that is given as S0 H0 plus n tilde of 0, that is the symbol of user 0 times the channel coefficient of user 0. R1 equals S0 H1 plus n tilde of 1. Similarly, R of L minus 1 corresponding to the Lth path is S0 H L minus 1 plus n tilde of L minus 1. Each of these noise components is additive white Gaussian noise of variance sigma n tilde square divided by n. Remember, n is the processing gain, so each noise power is suppressed by capital N. Hence, this noise power is sigma n tilde square divided by capital N. So, I have 0, 1 up to L minus 1 path. So, I have extracted the components corresponding to L paths. Now I can vectorize this by making vector r bar. Let me denote r0, r1, r l minus 1 by the vector r bar, which is equal to h0, h1, hl minus 1 divided hl minus 1, which I will denote by h bar, which is now denoted by this vector h bar, times s of 0, that is a symbol transmitted for user 0, plus n tilde 0, n tilde 1 up to n tilde l minus 1, which is n tilde bar. Okay, so now I have vectorized this system. I can denote this as r bar equals h bar, or let me also make this as h0 bar to denote the channel of user 0, times s of 0 plus n tilde bar. Now, if you look at this expression is nothing but the expression previously we had for diversity. That is, remember we said we are going to consider a system in which there is not a single link, but there is L links. Each one has coefficient h0, h1 up to hl minus 1. These were the coefficients of the L links, and then we employed the maximal ratio combiner to combine the signal components received from these L links, which we said could be L antennas, and we combined them so that we can maximize the SNR at the receiver, and we said this has a diversity order of L, and hence the probability of bit error decreases as 1 over SNR to the power L, hence it results in a very low bit error rate. Now, in CDMA, remember we do not have multiple antennas. I mean, this is not a system with multiple antennas, but only multiple paths, but by correlating with each path we are able to extract each of the paths. So, each of the paths is acting as if it is a different link. Now, I can coherently combine the signals corresponding to these different links to enhance the SNR at the receiver, and that is the principle of the rake receiver. So, in the rake receiver I will form my net statistic R, which is W bar Hermitian R bar, that is I am taking R1, weighing it by W1 conjugate and combining it. I am taking R2, weighing it by W2 conjugate and combining, so on. I am taking WL minus 1 conjugate and combining it, L minus 1 conjugate, and this should also be W0 conjugate R L minus 1. Okay. And we said the optimal W bar to use in the maximal ratio combiner is nothing but W bar optimal, that is the W bar that maximize the SNR, is nothing but H bar divided by norm H. This is the W bar that maximizes SNR at output. And we also said during our MRC we derived that the SNR at output after the maximal ratio combiner is nothing but norm H 0 square times P, which is the transmit power of user 0, I will denote this by P0, divided by the noise variance, which is sigma n square divided by n. Remember, the spreading gain results in a suppression of noise power, hence the SNR is nothing but n times norm H square times P0 divided by sigma n square. This is the SNR. This is the SNR at the output, SNR at the hence this is the SNR at the output of the rake receiver. Okay. So, let me just expand on this a little bit. The SNR is nothing but norm h square n p over sigma n square. I will write norm h square as h0 square, coefficient combining to path corresponding to path 0, plus h1 square, coefficient corresponding to path 1, plus HL minus 1 square times n times P0 divided by sigma n square. Sorry, the square root will not be there. So, this is nothing but norm h square. So, look at this, I am taking whatever is transmit SNR and I am multiplying it with the sum of the energy with of each path. Look at this, h magnitude h0 square is nothing but the gain of the path 0 corresponding to coefficient 0. I can think of it as the energy that I receive from path 0. Norm h1 square is nothing but the gain corresponding to path 1. So, I can think of this as the energy I receive at the receiver corresponding to path 1, so on and so forth up to magnitude HL minus 1 square. So, I am combining the energies that I am receiving from these L paths, hence that is nothing but diversity. Remember, I am coherently combining these things. So, I am able to extract more power and precisely L times more power than what I could have extracted before without the rake receiver, hence this results in a significant improvement in performance. In fact, we know exactly what the performance looks like. We said the bit error rate now decreases as 1 over SNR to the power of L, thanks to the diversity gain provided because you are extracting reliability from this system. And so let me make a note of this point. So, the rake receiver, so let me make a final note of this point, the rake receiver extracts multipath, remember this is the key point, extracts multipath diversity through coherent combination. Remember, we are combining them coherently, coherent combination of the multipath components. I am coherently combining the different multipath components through this rake receiver, and hence I am able to extract multipath diversity, which is remarkable, which is not possible imagine in systems previous to CDMA such as GSF. Well, there are other schemes to extract diversity in them, which is through slow frequency hopping and so on, but CDMA gives you a very intelligent and a very straightforward and convenient way to extract multipath diversity, which is simply by taking the received signal and correlating it with shifted versions of the spreading code corresponding to the desired user, and that helps you extract multipath diversity. So, that is another mode to extract diversity which is unique to CDMA and hence results in very high performance gains in CDMA system because it lowers the bit error rate, and hence this is the fourth advantage. Remember, we started by listing advantage. This is the fourth advantage of CDMA systems, which let me again summarize. Fourth advantage, number 4 of CDMA systems is that they enable extraction of another advantage of CDMA systems is that they enable extraction of multipath diversity through rake receiver. Okay, so that is the advantage of CDMA over previous 2G systems and so on. All right. Okay, so that completes one part of the lectures on that completes one part of the lectures, which is the advantage of CDMA. Now I will move on to comprehensively analyzing the performance of a CDMA cellular network or the performance of a multi-user CDMA system, and we will do that both on the downlink and the uplink. So now we will start with the next subtopic in CDMA, which is performance of CDMA downlink scenario with multiple users. All right, what is the received SNR in a multi-user CDMA system when on the downlink, which is when the base station is transmitting to the different users. So let me start with a basic description of the downlink scenario, although you might be familiar with it from your first course on mobile communications. So let me start with a brief description of the downlink scenario. The downlink scenario is nothing but where the base station is transmitting to several mobile users. So this is the base station, it is transmitting to several mobile users. The direction of transmission is from base station to the user. All right. So this is the direction of transmission. This is downlink or a DL scenario where base station is transmitting to several mobile users. Let me call this user 0, user 1, user 2 and so on. Okay. So what the base station does, remember in CDMA there is no division in terms of time or frequency, but it is division on the basis of code. So all symbols, all the information symbols of all the users are combined using different codes, and then they are simultaneously transmitted on the downlink. That is, these different signals are essentially multiplexed onto the same signal and then they are transmitted on the downlink. So let me start with that system model. Let me consider k users. So let us consider k users, that is 0, 1, 2 up to k. These are, so in effect these are capital K plus 1 users, because I am counting from 0, 1, 2 up to k. Now we will use the standard CDMA notation in which I will represent by 0 the desired user and by 1, 2 up to k as the interfering users. Now there is nothing special about user 0, it is just for notational convenience that I am going to represent desired user as user 0 and the rest as interfering user. In fact, if you would consider decoding at user 2 will be the desired user and user 0 1 and user 3 to capital K will be the interfering users, and so on and so forth. So, and the expressions are going to be symmetric. I mean, what happens at user 0 is the same thing as what happens at user 1 at user 2. So, these expressions are symmetric. So, it is essentially instructive to derive it at one user, and the rest of the users you can appropriately derive by similarity and symmetry. Alright, so let us consider user 0 as the desired user and user 1 to capital K as the interfering users. That is what I am saying in this figure, is that user 0 is the desired user, and the signals that are transmitted to user 1, user 2, etc. also interfere at user 0. We are going to see how that happens. Now, the symbols transmitted of the K users, let the symbols, the information symbols symbols transmitted to the K users are S of 0, S of 1, S of capital K. S of 0 is the symbol transmitted to user 0, S of 1 is the symbol transmitted to user 1, so on and so forth up to S of K, which is the symbol transmitted to user K. And since we are saying 0 is the desired user, this is the symbol transmitted to the desired user, and this is the these are the symbols that are transmitted to the other users who are also sharing the resources or who are sharing the same interface in this CDMA system. Now, the codes of different users again will be using the same standard notation. C0 is the code of user 0, C1 is the code of user 1, and so on. Ck is the code of user K. So, this is spreading code or the CDMA code of user 0, and these are codes of users 1 to up to K. Now, what I am going to do is I am going to take the symbol of each user and multiply it by the code of that corresponding user. Remember, that is what we do in CDMA. We take the information symbols, multiply them with the code, add all these streams up and transmit them on the downlink, because that is what we are saying. This is code division for multiple access. So, since it is code division for multiple access, we differentiate the users on the basis of code. So, the signal x0 of m, this is the signal of user 0, which is equal to S0 into C0 of m, that is symbol of user 0 into code of user 0. X1 of m is the signal of user 1, which is symbol of user 1 into code of user 1, so on and so forth until x capital K of m, which is the signal of user K, is the symbol Sk of user K and the code Ck of m of user. So, essentially x0 of m, which is the signal of user 0, is his symbol S0 times the code C0. S1 or x1, the signal of user 1, is S1 symbol of user 1 times C1 code of user 1, so on. Xk, which is the signal of user K, is symbol Sk of user K times the code Ck corresponding to user K. Now, what I will do is I will sum up all these signals, that is the and form a composite signal and transmit it on the downlink. Remember, this is what I did, this is what we did before in CDMA, the very first lectures that we said the symbols are multiplied by the codes and they are transmitted, this composite signal is transmitted on the downlink. Each user correlates with his code and extracts the corresponding signal. So, the composite transmit signal on the downlink of this CDMA system is nothing but XM, this I am denoting as the composite signal equals x0 of m, signal of user 0, plus x1 of m, signal of user 1, plus x capital K of user m, which is the signal corresponding to user K. This is nothing but summation I equals 0 to capital K x I of m, that is I am taking all the signals corresponding to the different users, summing them and making a composite signal out of it, which will be transmitted on the downlink. Now, x I of m is nothing but signal of user I, which is SI symbol of user I times CI, that is code of user I. Since I will write this as I equals 0 to capital K SI times CI of m. Remember, again let me just write over here, this is symbol of user I and this here is the code of user I. Alright. So, I am taking all the symbols corresponding to the different users, multiplying them by their respective codes and then summing them up, transmitting it on the downlink. Alright, that is what we do in CDMA, that is code division for multiple access. Now, let us go back to, now given this transmit signal, let us go back to what happens at user 0. The signal received at user 0 will be the composite transmit signal that is received at user 0. Remember, we are transmitting a composite transmit signal, that is the sum of the signals of all users. Hence, the signal received at user 0 on the downlink will travel through channel H0. However, user 0, because it is CDMA and because I am transmitting the signals of all users together, user 0 will not only receive his signal, but he will also receive the signals corresponding to user 1 and 2, from which he has to extract his signal by correlating it with his corresponding code. Alright, this is a slightly subtle point which does not happen in GSM or other systems, essentially because CDMA, because in GSM there are different time slots in which user 0 receives his signal. However, in a CDMA system, because we are transmitting a composite signal in all time and frequency, every user on the downlink receives this composite signal which contains the signal of every other user. That is the essential idea in CDMA, and from that user 0 extracts his signal, user 1 extracts his signal, user 2 extracts his signal, and so on and so forth. So, from this composite received signal, you extract, each user extracts his corresponding signal. So, let us go back to that and let us represent that mathematically. We will assume the multipath channel, or let H01, H02, H0L minus 1 denote the L tap multipath channel between the base station and user 0. Denote the L tap multipath channel between the base station and we are saying H0 or I am sorry H0 0, H01, H0 L minus 1, that is H0 0, H01, H0 of L minus 1. These are the L taps or these are the L coefficients corresponding to the L taps of the multipath channel between the base station and user 0. So, we are saying this has L multipath components between the base station and user 0. Hence, the output of this multi-tap channel, the received signal as output of this multi-tap channel, which is the received signal at user 0 through his channel H0 is nothing but, through his channel H0 is nothing but H0 of 0 times x of m, this is the composite signal, plus H0 of 1 times x m minus 1 plus H0 of 2 times x m minus 2 plus so on up to H0 of L minus 1 x m minus L plus 1. So, the signal y m which is received at the output at user 0 is nothing but H0 of 0 times x m, that is depends on the current symbol, but we said this is an inter-symbol interference channel because this has L channel taps, hence it is H0 of 1 into x m minus 1 plus H0 of L minus 1 into x m minus L plus 1, similar to what we have seen before. So, x m is the desired symbol and x m minus 1 so on up to x m minus L plus 1 are essentially the symbols that are interfering with this symbol. However, as we saw previously, we can now use a rake receiver in CDMA to conveniently separate these different components and coherently combine them to extract diversity, which is what I will derive now. Hence, this is an inter-symbol interference or this is an ISI channel. Of course, there is also going to be noise here. So, this is received in the presence of noise. Alright, so I can succinctly represent this as y m equals sigma d equals 0 to L minus 1 H 0 of d x of m minus d plus n of m, that is I am taking this expression and replacing it with a summation which is H 0 of d times x of m minus d plus noise. Alright, so, this I am simply replacing it by the summation. Now, x m I will represent it by the composite signal. Remember, x m is nothing but summation of s k c k of m, hence this becomes summation d equals 0 to L minus 1 summation small k equals 0 to capital K. Capital K is the total number of users, small k is the index in this summation. So, please remember that. Okay. So, H 0 times d, x m is nothing but summation s k c k of m, hence this becomes s k c k of m minus d plus n of m. So, the received signal is H 0 d Sk Ck m minus d summation over k equals 0 to k, that is all users, since this is a composite signal, summation over all the paths d equals 0 to L minus 1 corresponding to user 0, since this is a multipath channel. So, there are two summations, one with respect to the paths, one with respect to the users, plus n of m. So, this inner summation is related to users and this outer summation is related to multipath. But remember, this is multipath of user 0. So, the outer summation is multipath of user 0, because we are considering decoding or processing at user 0, who is the desired user. Okay. So, now what are we going to do next? We know that at user 0 we have to correlate with C0, that is the code corresponding to C0. So, that is the same thing, that will not change. So, what we will do is we will correlate this with C0 of m at user 0, that is how the user 0 processes his signal. So, at user 0 correlate with C0 of m. With C0 of m, that can be expressed as, let me denote the output of that correlation as R0, that is nothing but 1 over n summation m equals 0 to n minus 1 y of m times C0 of m. So, this is simply the correlation of y of m with C0 of m, that is I am taking y of m, correlating it with the code sequence corresponding to user 0, that is R of 0. Now, this can now be expanded using your previous expression for y of m. I can expand this as follows. This is nothing but, remember, y of m is H0d Sk Ck m minus d. So, I will expand this as 1 over n summation d equals 0 to L minus 1 summation k equals 0 to capital K minus 1 summation m equals 0 to n minus 1, where capital N is the number of chips, H 0 d Sk Ck m minus d into C0 of m. This is the signal corresponding to the paths of user 0 corresponding to all k users, that is a composite signal. Now, I am correlating this with C0 of m, that is the code corresponding to user 0 at user 0 to process the received signal for user 0, plus of course, there is going to be a noise component which is 1 over n summation m equals 0 to n minus 1 n of m into C0 of m. Now, first, since it is easier, let me start by analyzing the noise component, because this is nothing new. This is what we have seen several times before. This is the noise component. This is what we have seen several times before. This is the noise component. So, the noise component, let me denote this 1 over m sigma m equals 0 summation m equals 0 to n minus 1 n of m C0 of m as n tilde of 0. So, I am denoting this by n tilde of 0, similar to what we had done before, that is output of the noise after you correlate with the sequence of user 0 shifted by 0, that is C0 of m, that is there is no shift, that is what this 0 is. 0 indicates that there is no shift, similar to what we did in the rake receiver. We know that this noise variance, this noise is additive white Gaussian. First of all, look at this, this is a linear operation. When you take Gaussian random variables, add them up linearly, the output is still Gaussian, hence this noise n tilde 0 is additive white Gaussian in nature. The variance of this noise is, as we have seen many times before, that is nothing but sigma n squared over n, that is the noise is suppressed by the processing gain, hence the variance of this is sigma n squared over n. This is the variance of the noise at the output. So, this is the variance or power of the noise at the output. This is nothing but the variance or the power of the noise at the output. Now, let me come back to the main term here, which is the signal component. This is the signal component. This is the signal component. Let me come back to this main term, because this term is slightly larger and it requires some understanding and analysis. So, let me spend some time over that. Let me rewrite again the signal term. The signal term is nothing but 1 over n summation d equals 0 to L minus 1 k equals 0 to capital K minus 1, m equals 0 to capital N minus 1 h 0 of d, s k c k of m minus d times c 0 of m. Okay, I am taking the total composite signal received at user 0. I am correlating this with the code corresponding to user 0. Now, because this is a composite signal, first let us understand this. This has the signals corresponding to all the capital K users, that is 0, 1 up to capital K, in fact capital K plus 1 users. And remember, the channel of user 1 is a multipath channel, which means there are 0, 1 up to L minus 1, that is capital L components. Hence, the total number of components in this received signal is nothing but L components corresponding to each of the capital K plus 1 users. Hence, this has total K plus 1 times L components. Hence, let me make this observation: the received signal in CDMA downlink at user 0 has capital K plus 1 times L components, has capital K plus 1 times L components. Out of this, L of the components corresponding to signal of user 0. Alright, L components, that is L multipath components, correspond to the signal of user 0 corresponding to coefficients h 0, h naught of 0, h naught of 1 until h naught of L minus 1. The rest capital K times L components correspond to the L components of each of the interfering users 1 unto capital K at user 0. Okay. So, out of these K plus 1 into L components, out of this K plus 1 times L components, L components belong to user 0. Those are nothing but his multipath components, and capital K times L components belonging to the rest of the capital K users. To the rest of the K users or essentially the K interfering users. Now, each of these capital K times L components are on a different code. Remember, the signal of each of the other capital K users, which is 1, 2 up to capital K interfering users, is on code C1, C2 up to Ck. Hence, when you correlate with C0 of M, they look like noise, and hence it is orthogonal, hence they act with expectation 0 and noise variance 1 over n. So, roughly speaking, these capital K L components correspond to each a noise of variance 1 over n. So, each contributes a power or each contributes an interference of power 1 over n. Now, out of these L components of users, so each components, each capital K L components of the rest of the users contribute interference 1 over with power 1 over n. The rest of the L components of user 0, out of these L components, one component which corresponds to path 0 is extracted by correlating with C0 M. The rest L minus 1 components, because remember these are shifted components. So, when you correlate with C0 of M, they also contribute interference of power 1 over n. So, these L components further split into component corresponding to H of 0, which gives signal S of 0 times H naught of 0, and the rest of them contribute to interference, that is L minus 1 components contribute to interference of 1 over n, interference power 1 over n. So, out of this capital K plus 1 times L components, except one component which is extracted by correlating with the code of user 0 C0 M, the rest all act as interference. L minus 1 components are interference from the multipath components of the same user. The rest capital K L components are interference from the multipath components of the interfering users. So, this is the intuition essentially for the downlink CDMA scenario. Because of the shortage of time, I will stop at this point and we will start the next lecture at this point and continue this discussion further, where we will derive the actual SNR expression seen at user 0, that is the desired user. Thank you very much.